Hello once again, Mr. Wakefield here, looking at Chapter 9 and in particular 9.2 right now. And we got this concept here called composite function. Composite function, I know it looks like multiplication right here, but that is not multiplication. If you look really closely at that, what you see there, it's not a multiplication symbol, but it's actually an open circle, all right, as opposed to just a dot like you normally see for multiplication. This is called F circle G. F circle G also could be called F composed with G, which is why they call it a composite function. And what you do is instead of plugging a number into a function, you're actually plugging an entire other function into that same function. And that's what it means to have a composite function. Don't worry, we'll explain that very carefully here coming up. But that's what it's all about. Yeah, but no matter what, and let's just back up here for a second. Usually when we have a function, we call it f of x, right? And we saw that back in Chapter 2 on a number of occasions. In particular, Section 2.1, we talked about how when you plug in a number into f, all right, whatever that number is inside that bracket next to f over here on the left, that goes into wherever the variable was located over here on the right, okay? And so that goes into this thing right here, all right? And the 3's went into the x right there from that function. Let me zoom out a little bit here. There we go. So whatever goes into this spot right here, in this case the 3, goes into the spot where the x's were over here. So you got the 3 and then the 3 and the 3 there. Okay. Now, what does that have to do with this? Well, instead of having, say, for example, f of 3, all right, you now have f of g of x. F of g of x, all right? So what is the difference there between those two things? In order to fully understand the difference between these two things here, let me use some color here, all right? I'm going to change not change it, but I'm just going to put the 3 in red there, and I'm going to put the g of x also in red. Oh, almost didn't do that there. Hold on. There we go. I want to emphasize that, first of all, when it says F circle G, it means that the first function stays on the outside of this bigger bracket. You see how we got two brackets here, the one with the X and then the bigger one? When you have F circle G, the first function, which is F in this case, is going to be on the outside, and the second one goes on the inside of the bigger bracket along with its X right there. So what I want to emphasize here is that just like when you plug in a regular number like 3, all right, you're going to plug in g of x now this time, all right, whatever that's equal to. And don't worry, we'll mention that about how that works exactly with more detail when we get through this first problem here. Let's go jump down to that first problem and we'll talk about it. F circle G means what? F circle G again means, and it actually asks us 3 questions here. This is the first one. F circle G of x. All right. And again, when you have that circle thing, the one that's in front of the circle and one that's behind it, the one that's in front of it goes like it goes outside the bracket. The one that is after the circle, in other words, the second one, that goes inside of that along with the x, like this. Okay, just as a comparison, you guys, what happens if the G goes first and the F goes second? G circle F. Let's write that down, just so you can see how it works. No matter what the order of the letters are. Okay, again, when you have the circle function, the first one is on the outside. The second one goes on the inside along with the X right there. Okay, so F circle G, F goes on the outside, G goes on the inside. G circle F, the G goes on the outside, the F goes on the inside. The first one always on the outside, the second one always on the inside. Now, what I'd like you to notice here again is the G is on the inside, just like if you have a normal number on the inside. What we want to do at this point, though, after we write it in this form with the first one on the outside and the second one on the inside, is I want you to change the inside to what it's equal to. The g of x is the same thing as x minus 5, so I'm going to change the g of x to x minus 5. You do not need to put it in red, okay? I just did that. There's a very good reason why I did that. It's kind of similar to what I just talked about at the top of the page. All right, but you can just write x minus 5 like normal, but change the g of x to whatever it's equal to, because that's ultimately the thing that you're going to plug in. You're not going to plug in the actual letters gx, all right? You're going to plug in whatever it ends up being equal to, which is x minus 5 in this problem. Okay, now, f of x minus 5, just like I was talking about at the top of the page. This is not part of the problem. This is just to help you understand. But let's just pretend like we're plugging in, say, the number 3 again. Okay, what is f of x in this problem? I'm not talking about f of g of x. I'm just talking about f of x. Okay, because see here how we have f and then we just have a number 3. So when you have just a number, all right, or anything that's inside of the bracket next to the f will go into this spot right here. In fact, I'll go ahead and put the red one right here too. All right, whatever's inside of the bracket next to the f, that goes into this spot over here. All right, just like we learned in chapter 2. Whatever goes inside of that bracket, here we go again, whatever goes inside of that bracket from chapter 2 will go inside of the x over on the other side of the equal sign. All right, so if the 3 goes there, then the 3 goes here and here. All right, same thing. So that means that this is going to be 3 times 3, isn't it? Follow me here. F of 3 is 3 times 3. Whatever goes inside that bracket next to the f goes inside of the x over here. All right, why am I emphasizing all of this? It's because what's inside in the actual problem that we're doing right now, what is the thing that's inside of the bracket next to the f? It's not just a normal number this time. It is x minus 5. But you still do the same thing, you guys. Whatever's inside of that bracket goes inside of the x on the other side of the equal sign. So then the answer then is going to be this right here. You don't have to put this in red, but again, just to make sure you're seeing it. Colors always help see things better. Okay, I'll put it in red right there. So whatever's in the bracket next to the f, even if it's something that's not just a number but it has a variable in it, okay, that thing will then go into the variable over here. And you always got to replace the variable with a bracket, just like we did in chapter 2. Replace the variable with a bracket before you put the thing in there. In this case, it was just the 3 we put in there. All right. But speaking of that, back in chapter 2, we even saw stuff that had variables in it. But again, it was still the same idea as it is right now. All right, whatever's in that bracket next to the f, that goes inside of the bracket over on the other side, where the brackets on the other side that replace the variables, that is, it goes inside of those brackets. All right. Same thing here with the x minus 5. You can leave the answer like that. I'm okay with that, but you could also distribute this out. It's good either way. You could circle this answer as well. All right, now, again, what do we do when we do a circle function? Even if the g goes first, all right? What you do after you put the first letter on the outside and the second one on the inside, like we talked about, just like we did in the first part here, we take the inside part. The outside part stays the same on this step, but the inside part, what you do is you change the inside part, which is f of x, you change it to whatever it's equal to. Just like I changed the g of x to x minus 5, whatever's on the inside, change it to whatever it's equal to. In this case, the inside is f of x, so we change that to 3x. Again, red pen is not necessary here. Just trying to help you see it. So, what do we got here? Again, whatever is inside of the bracket that's next to the g right here, whatever's in there, it could be an x, it could be a 3, it could be an 8, it could be any number, it could be anything even with a variable in it. Whatever that is, you put it into this spot, because you always take whatever's inside that bracket there and put it wherever the variable is on the other side of the equal sign, just like in chapter 2. So if it's 3x that's inside of that bracket next to the g, then that means that we take that's like the 3x, that's like the 3x being right here, isn't it? Okay, the 3x is now inside of there. Okay, whatever's in there, no matter how big it is, that 3x then would go here. If there was a 5x in there, the 5x would go here. If there was something really big like 7x squared plus 2, okay, if that whole thing is inside the bracket, then 7x squared plus 2 would go there. No matter what's inside of there, that goes there. And so this is going to be like that, okay? Remember, use a parenthesis to replace your variable and then put the thing in there that's supposed to go in there. In this case, it's 3x because that's what's inside the bracket next to the g. All right. Because it's g on the outside, that's why I picked this formula with the g. Because the first problem had f on the outside, that's why I plugged it into this one. All right. So you gotta know. Obviously, you gotta follow which variable is on the outside. If it's f, you pick this one. If it's g, you pick this one. And so you can leave your answer like that. You could also just say 3x minus 5. All right. The bracket, when the bracket's at the beginning of the problem and there's not an exponent attached to it or anything, and in fact, if the bracket's at the beginning of the problem with nothing in front of it and it has nothing behind it other than maybe an addition or subtraction symbol, then you don't even need the bracket there. If it's being multiplied by something, that's different, front or back of the bracket. But if it's nothing in front of it and just a plus or minus behind it, you don't need the bracket. You can keep it if you want to, though. Okay. Now, this last part here says f circle g of 2. There's a couple different ways you could do that. Let me write that down first. Okay, we know that when you have f circle g, that means that f goes on the outside and g goes on the inside. But the difference is that because the x is no longer in the original statement there with f circle g, you don't have x next to f circle g this time, but you have 2 next to it. We're now going to put the 2 where the x would normally go. See how the x went here? X was here, x was here. Well, now that 2 is in that first spot where x originally was, the 2 will now go on the next step in the same spot where the x originally was. And so we get f of g of 2. We do the same thing, you guys, all right, that we did in the previous 2 parts. You first of all figure out what g of 2 is equal to, and then you plug it into f. So figure out what the inside is. We did that up here when we figured out that f of x was 3x, and we figured out that g of x was x minus 5, and then you plug it into the outside function. Figure out the inside function, plug it into the outside function. That's what it's all about with these composite functions. G of 2 is what? And remember, it just says g of 2, all right? It's not f circle g. We're just talking about the inside only right now, so no f yet, okay? G of 2 is 2 minus 5, isn't it? All right, so because there's no f that we're talking about yet, we're just looking at this. And so what is 2 minus 5? That is negative 3, right? So figured out the inside, like that. And then, what does that give me here? Now that I know what the inside is, I'm supposed to plug it into the outside. All right, just like I did with x minus 5. F of x minus 5 was 3 times x minus 5. In a similar way, and I already have it written down up here. Okay. Oh, I'm sorry. I plugged in. Oh, no. I don't have it written down up here. I got the 3 and the negative 3 mixed up. I apologize. So yeah, you figure out the inside, you need to plug it into the outside, and just like we did with x minus 5 going into this thing next to the 3 here, now since the inside of the bracket next to the f, since that's equal to negative 3 this time instead of x minus 5, we're now going to have 3 times negative 3. Let's write that down. 3 times negative 3. So the final answer there is just simply negative 9. We didn't plug in a variable this time, so it's not a surprise that the answer doesn't have a variable in it either. Okay. All right. So moving on to the next problem here. Again, what's the key thing that we need to remember? No matter whether you do F circle G or G circle F, all right, you always figure out the inside function, which is the second function, and then you plug it into the first. So let's set it up. Part I, it's asking for this right here, and that is going to be what? That is going to be the first function on the outside, the second function on the inside. After you set that up, you then take what? You then take the inside function and you figure it out. And they already tell you, but you figure it out and you put that in there. All right. So that's going to be what? That's going to be, since g of x is the same thing as x plus 3 over 6, that's the thing that's going to go on the inside of the bracket there. All right. And then what do you do after you figure out the inside function? All right, you plug it into the outside function. All right, so whatever goes inside of here, even if it's some big fraction like x plus 3 over 6, whatever that is, that goes right here. All right, it goes wherever the x is on the other side of the equal sign. So my final answer, well, not final answer, we can still simplify the answer, but I need to plug it in to wherever that is. And again, use a parenthesis here. And again, I'll be consistent here, do my red pen here again. Okay. So I'm going to plug that in. Plug it in wherever the x is on the other side of the equal sign from where the f of x is. And everything else stays the same like it normally does when you plug into a function. All right, just replace the x with whatever's inside the bracket. And the 6 and the minus 3 are still there in their same location. Let's go ahead and simplify this. And there's a good reason for that, as you'll see coming up here. But how do we simplify it? Even though we have a variable in this answer, we can go ahead and do something that's similar to order of operations, where if this had been like a normal number here instead of having a variable in it, like if it was a normal fraction without a variable in it, we would multiply by 6 before we subtract the 3, because multiplication comes before subtraction. And let me even back up even further than that. Since there is a variable in there, we still do PEMDAS. We still do the, parentheses first, and then the multiplication, and then the subtraction. It's just that we can't do anything with the parenthesis because of the x. All right, you can't figure out what that fraction is equal to, so you just leave it alone. All right, you skip the parenthesis step. That means we then do the multiplication. And when we multiply, the 6's cancel right there when we do the multiplication right there. And we end up with this right here. X plus 3 over 1. You don't need to write over 1. And then the minus 3 is still there. That's behind that multiplication. And so now I need to take x plus 3 and subtract 3 from that. And when we have a polynomial minus a term like that, no parentheses or anything, just a polynomial minus a term, that means to combine like terms. Okay? And that would just end up being equal to x. There's a significance to that. All right, whenever your composite function, whether it's f circle g or g circle f, whenever it's equal to x, in fact, if both of them are equal to x, which you're going to see that they do end up both being equal to x here, there's a significance to that that's going to lead us through the rest of this section here. So it's important to understand that as well. We'll get into that. First things first, though, what is g circle f? I already gave away that it's going to be equal to x, but why is it? All right. Again, the first function goes on the outside. The second function f goes on the inside. We then figure out what the second function is equal to. The second function is equal to 6x minus 3, so we replace the inside of the bracket with 6x minus 3. And then just like we've been doing, once you figure out the inside, you then plug it into the outside function. The outside function is this right here. Okay, so whatever is inside of that bracket that's next to G right there, that goes here, doesn't it? Always put it into the variable on the other side. So we get what here? We end up getting, got to plug it in here. I'm just going to write down the rest of it here before I plug it in. But I got to plug in what? I've got to plug in 6x minus 3, like that. And then that's what we get for the composite function. We just need to simplify this now. Again, order of operations says that when you have just one big fraction here, you figure out what the top and bottom are equal to, and then you put it in lowest terms. If I figure out what the top is equal to here, whenever I have a bracket that's not being multiplied by anything, but just a bracket with nothing in front of it and just a plus behind it, similar to what I said over here, you can get rid of the bracket, but even more importantly, to getting rid of the bracket here is that you can then combine like terms. Because if you get rid of the bracket, it's just going to be a bunch of terms being added and subtracted together. And that means to combine like terms if there's no brackets there, which theoretically we can get rid of it, like I said. So 6x minus 3 plus 3 combines to be just 6x, isn't it? But we know that when we have a single term divided by a single term, you can cancel in the normal way here when you have single terms. Just cancel the 6 and the 6, reduce that, and that, as I promised you, would end up being equal to x after you simplify it. Okay. There is a special name that they have for composite functions when both f circle g and g circle f, when they're both equal to x. That means that f and g individually, those two individual functions, f by itself and g by itself, those two things, those two functions are inverses of each other, meaning that g is the inverse of f and f is the inverse of g. They're inverses of each other. You can see that we talk about that up here. Okay, if both of these things are equal to x, then g is the inverse of f, all right, and vice versa as well. Like I said, f is the inverse of g, all right. We'll talk about that more on the back side of the worksheet about inverses, but for the moment, let's answer that last question again. If you plug in 2, all right, yes, I know that there's more than one way to do this type of situation here. If you want to do it a different way, as long as you're sure you know what you're doing and you show your work, that's fine. But I'm going to do it this way because I want to make a point here that's important. We're going to do it the same way I did in the last problem, in other words. G of 2 is what? Figure out what the inside is equal to first. Okay, what is G of 2? If I plug in 2 right here, it's going to be equal to 2 plus 3 over 6. What is that? 2 plus 3 over 6. Isn't that equal to 5/6? 5/6. And so that means that the inside of the bracket is 5/6. All right, now, what do we do after we figure out the inside of the bracket? We plug it into the outside function here, the first function from over here, which is f, and what do we get? So I plug in 5/6 right here, which means I plug in 5/6 right there. Let's see what happens. And I forgot to do my color there, but I think you can see my point here. I'll just go ahead and write it down anyway. 5/6. There we go. And again, doing order of operations, we multiply before we subtract. 6 over 1 times 5 over 6. The 6's cancel. and we get 5 minus 3. 5 minus 3 is 2. Not a surprise that it ended up being equal to the original number that we plugged in, because the original number is represented by x, and it was supposed to end up being equal to x, and so whatever that x was equal to, that should be the answer. All right, but there's a significance to that here, all right, with inverses, and that is the fact that with inverses, whatever you plug into the composite function not only will be the answer, but something else interesting occurs as well. Notice that when we plug 2 into G, we got 5/6. Remember I talked about in chapter 2, when we first talked about plugging numbers in, is that when you plug a number in, that number is your x. And the answer that you get is the y value. So like if you were to graph it on like a graph with an x-axis and a y-axis and everything, which we didn't do here, but I'm just saying if we did, then the x would be the 3 and the y would be the 17. Okay, so in a similar way, for the G, you don't have to write this down. This is not part of the problem, but it's going to help us on the back side of the worksheet here. For the G, 2, 5, 6 is one of your ordered pairs. If I said, hey, I want you to graph G of x, that would be one of the points on the graph. Because you plugged in 2, all right? You plugged in 2, and you got 5, 6 as an answer. Okay, now here's what's interesting, though. Notice how I plugged 5, 6 into F, didn't I? So now the 5, 6 becomes the X, all right? Because it got, just for the F, though, not for the G. For the F, since I'm plugging into F, the 5, 6 is now the X that goes with the F function, because it's the number you plugged into F. And then what answer did I get when I plugged 5, 6 into F? I got 2. And so remember, the answer that you get when you plug a number into F, that is the Y. What's interesting about these two results right here that I'm pointing at right here? They flip-flop, right? 2, 5, 6, 5, 6, 2. That's what inverses do. And we already talked about how these are both inverses of each other, F and G, because the answers are both equal to X. All right, so we know that these are inverses, but I'm here to tell you, and again, this is going to help us on the back side of the worksheet now. This is going to happen on all ordered pairs that you create for F and G. Not that we're going to create a bunch of them, but if we were to, all right, we will create some, though, on some of these problems. But whatever the G produces, the F will produce the same exact ordered pair, except for the X and Y switches. It flips. Okay, the X becomes the Y becomes the X. And so that's going to help us moving forward. So we'll get into that more, but I wanted to share that with you right now. On the back side of the worksheet, the first thing I want you to do is similar to what we just did. They want you to find f of g of x, which is the same thing as f circle g. All right, same thing. All right, and then g of f of x, which is the same thing as g circle f. They want you to find those two things. They don't have the third question this time like they did on the front, just the first two questions, f circle g of x and g circle f of x. And then they want you to determine if they're inverses of each other. What makes them inverses, you guys? Both of these answers have to be equal to x. If they're not inverses. If they are, then they are inverses. So that's how you answer that second part right there. So go ahead and try these out and then hit the play button and we'll take a look at those answers. Okay, number one here, again, f circle g. What you do is, and I don't have color on this one, but I think we're starting to get used to it now. F circle g, again, you figure out what the second function inside the bracket is equal to. It's equal to x minus 9. You then plug that into the f. And so the x, I'll go and use color on this part. The x, whatever goes in that spot of that x there, in other words, whatever's inside the bracket next to the f, that goes in this spot right here. So I did that. I put the thing that's inside the bracket into that spot right there. The 4 and the plus 9 are still in the same place. I then figure that out by multiplying and then adding the 9 after that. And the 4's cancel on the multiplication. I then combine like terms, and it's equal to x. Same thing happens on the other one here. All right. If you realize that the second function is on the inside, you then figure that out first. It's 4x plus 9. You then take the thing that's on the inside of the bracket and you plug it into the outside function, which is this over here. So the 4x plus 9 is going to go where? Because the 4x plus 9 is here, the 4x plus 9 has to go right there. Okay. I know that's kind of small there. There we go. So that gives me what? That gives me what you see right here. All right. So let's go ahead and simplify that. Order of operations says to figure out what the top and bottom are equal to first. Like we talked about, a bracket minus a term. And that's all you got is just a bracket minus the term. You just combine like terms. The 9's cancel. We get 4x over 4. And that is also equal to x. Since both of them are equal to x, f and g are inverses of each other. On the other hand, though, moving over here, similar looking problem here, but a different result. F circle g, again, the second function, you figure that out first. You then plug it into the first. All right. The first function there is 3x minus 7, so whatever's inside the bracket replaces the x there. So 3 times the bracket minus 7, and there you go, you have it right there. If I multiply, first, the 3 and the 7 don't cancel this time, so I just multiply the fractions like I normally would if nothing cancels, or if everything already has canceled. And I just multiply the 3 into the x plus 3, and then the 1 times 7. I get this fraction right here. I need to get a common denominator, though, so that I can then subtract these fractions. And so 7 over 1 becomes 49 over 7. And when we subtract fractions, we subtract the numerators. The denominator stays the same, and we get this right here. You can already see that it's not going to be inverses because this is not equal to x. But they still want us to figure out the other part here. Again, the second function gets plugged into the first, so g circle f. You plug in the f function, 3x minus 7. You plug that into the outside function, g, and you get this right here. Okay, because g is x plus 3 over 7. So it ends up being bracket plus 3 over 7. All right. So I plug that in. I combine like terms on the top. I can't cancel anything here, so that's as far as it goes. All right, 3x minus 4 over 7. Because f and g are not equal to, pardon me, I said that wrong. Because the two composite functions, f circle g and g circle f, because those two things were not equal to x, they're equal to these two fractions instead, they are what? They are not inverses of each other. All right, so now we know how to figure out not only composite functions, but also figure out whether or not they're inverses of each other. What I want to do now is, speaking of inverses, let's say that I just give you one function and I said, instead of checking to see if it's an inverse with a different function like we did up here, where we already had two functions, we just had to check to see if they were inverses of each other. What if I just gave you f only and you had to find the inverse function that goes with it? Okay, that's the inverse function of that. How do you find the inverse of a function if you're just given the function and that's it? What you do is, let me pull out my clean sheet of paper so we can do it by hand here. There is a set of steps on the front side of your worksheet that explains this. 4-step process. First thing you want to do, because you never want to move f of x around and mix it with other stuff on one side of an equal sign. What we want to do is we want to replace the f of x with y. Okay, because y can be mixed in with different things on the same side of an equal sign, but not f of x. All right, f of x should always be by itself. And so I'm going to replace this with y, which is a perfectly legitimate thing to do because f of x is always equal to y, isn't it? We talked about that in chapter 2 also. That's step 1. Step 2 then is, what does step 2 say in the front side of the worksheet? It says to interchange the x and the y. Interchange the x and the y. That means that wherever you see the y, change it to an x. Wherever you see the x, change that to a y. Everything else stays the same. The equal sign, the 3, the -1, everything else is the same. But interchange the x and the y. Then what do? Then you get the new y, and please remember, you guys, this new y is not the same as the old one. The old one was f of x, all right? Because this new y is the same thing as the old x, as opposed to the old y, all right? They're not the same thing. This is the old y. The new y is the same as the old x. All right? Not meant to be the same thing, and they're not. So I need to get this by itself. How do I get that thing by itself right there? We talked about that also back in chapter 1. We talked about when you have more than one variable, you guys, inside of a equation. All right, when you got more than one variable inside of an equation, and you have to, let me just look at this one as an example. And if you need to solve for a particular one, in this case m, all right, how do you do that? If it's a polynomial equation, okay, just the normal terms, normal monomial terms on each side of the equal sign. Again, a little review of that. Just give me a second here. Just your normal monomial terms, no radicals, no fractions, none of that stuff, but just normal terms like this. All right. If that's all you got on each side of the equal sign, all right, then it's either going to be a linear equation, or it's a quadratic equation, or it could even be like a higher degree one, which we won't see here. Don't worry about that. This is going to be linear because it's m to the first power. If the variable is only to the first power and you don't have like m to the second, which would then potentially make it quadratic, then if it's just m to the first, all right, then it's going to be linear if you have a polynomial on both sides. This is a single term polynomial, and this is two terms being added together, two monomial terms being added together. That's a polynomial. Both sides are polynomials, m to the first. I'm just reviewing with you how to recognize what kind of equation you have right now. This is the same thing, all right? You just have a monomial and a polynomial, two-term polynomial here, because addition and subtraction separates it into two terms here, in this case subtraction. Because of the fact that it's y to the first power, this is going to be a linear equation. Okay, if you had y to the second, that'd be different. Okay, so what do we do in a linear type of equation? Just like with any linear equation, you take the term that had the variable in it, okay, and you put that on the opposite side of where the terms that don't have the variable in it, and I'm talking about the variable you're trying to solve for, all right, which in this case is m. You move the green ones to the opposite side of where the red one is by adding or subtracting. It's the same thing here in this current problem. I need to add or subtract the 1 over because the y is what we're trying to solve for here. So any term that doesn't have the y in it, that's green. And then any term that does have the y in it, that's red. So we need to get the green guys on the opposite side of where the red one is. X plus 1 is equal to x plus 1 because they're not like terms. Don't combine them. And then after you get the red term by itself, what do? Just like right here, after I got the term with the m in it by itself, I divide to get the m completely by itself. So in the same way, I divide by 3 here. The 3's cancel, and y is by itself. So we did it. So step 3 is to actually get y by itself right there. We did that. The last step, though, is this. It is to And this is going to look a little bit weird at first, so be patient with me here as I explain this. You're supposed to refer to your inverse when you find it. You didn't have to do it on those previous problems where we figured out if f and g were inverses. But if you find an inverse, okay, like we are in this current problem, we're supposed to call it f negative 1x. Now, I know that that looks like an exponent. It's not. Okay, it's just the symbol they use to indicate the inverse. This has nothing to do with exponents. All right, I kind of wish that they didn't use that symbol because it is kind of confusing to see that thing because it does look like an exponent. I apologize for that, all right, but that's the way that it's always been written in any textbook, so I certainly wouldn't want to change that on you. That'd be even more confusing to do it differently on this worksheet than it is in the textbook. So we're going to do it this way, but it just looks weird because it looks like an exponent when it's not supposed to be. So when you figure out what y is equal to at the end of step 3, you take that y and you replace the y with f inverse of x. That's how you say it. I'm not going to say f negative 1 because, again, it makes it sound like an exponent. This is f inverse of x. That's how you say that. And that is equal to this right here. Okay? Let's try that again now. Oh, by the way, before we do that, though, in your homework, when they ask you to find the f inverse of x, it says verify that it really is an inverse by showing these two things right here. You don't have to do this part. You don't have to do this part here. That's not going to be an issue in these problems here that we're doing on the worksheet or in the homework. If you do it the way I show you to do it, you should be fine. All right. So you don't need to do that part. It could be done, but it doesn't need to be done on your homework. So just keep that in mind. All right. Save yourself the time there. You don't need to do that. Problem B. First step. Change the f of x to y, just like we did in the last problem. Then, what did we do in the previous problem when we got to the second step? We interchanged the x and the y. So wherever you see the y, change it to an x. Wherever you see the x, change it to a y. Everything else stays the same. So the -1 and the bracket and the 3, they're all still there. And then step 3, what do? You get the y by itself. Okay. Remember, you guys, since we're getting y by itself, we are basically viewing or treating the x as if it's a constant number. Okay, only whenever you get a variable by itself, the other variables in the equation are thought of as constants, even though they don't look like it. Now, let me just show you a little bit of review of something we did earlier that's going to help us here. Remember the square root property here in the earlier part of this packet? In particular, a problem like this right here where you had a bracket squared equal to a constant. Okay, and what did we do? We then canceled out the exponent, and then we had the square roots right here. Notice this problem here looks very similar to that. It's the only difference, and it does look very similar because remember, we're treating x like it's a constant, just like 3 is a constant. The difference is that instead of having a bracket to the second power like we do over here, okay, we now have a bracket to the third power. So the rule is slightly different when you have a bracket to the third power equal to a constant, all right? The only difference is, and let me write it down over here, if you have either a variable, I'll call it m, just to not get it confused with the variables in this current problem. If you have a variable to the third power equal to a constant, all right, I'll just call it constant there. Then instead of doing the double square root, you still get rid of the 3, but instead of doing the double square root, you just do 1 cube root. The constant still goes underneath here, all right, but it's only 1 radical instead of 2, but it's a cube root because this is cube. Cube becomes cube root, all right? It does not matter if this is a variable or if this is a bracket like we have here, all right? So if you have a bracket to the third power, it's the same thing. Let me write that down. So the 3 goes away, just like you see right here, and then the 3 becomes the cube root of whatever's on the other side. So again, we're treating the x like it's the constant right here, and so the constant goes inside the radical, and then the 3 cancels out on this side of the equal sign, and it becomes the cube root over here on this side. All right. And so we did it. We got rid of that exponent. This is still a constant because y is not over here. Y is our variable. Since y is not over here, that's a constant. So this is no different than having y minus 1 equal to 7 or y minus 1 equal to 9 over here, all right? And just like any other constant, you would add the 1 over, okay, to get the y by itself, all right? Because this is a green, this is a green, all right? And this is a red. All right. This was not a polynomial equation up here because I had the brackets in it. And you need to clear out the parentheses first. And then if it's a polynomial on both sides. Normally this wouldn't be a polynomial when you have a radical. But because there's no variable there, you can think of that as just a constant term in a polynomial. So you got your reds and your greens. You need to get the greens on the same side. But clear out those parentheses first, okay, by using this property here. All right, don't multiply it out 3 times, all right, but use this property. When you have a bracket to the 3rd power equal to a constant, similar to the square root property. It's just that it's a 3 instead of a 2 now. All right, so we got this right here. We got that. Now that the y is by itself, we change the y to f inverse of x. So here's your final answer right here. Okay. Be careful that that bar doesn't go all the way over here, or otherwise it'll look like the +1 is inside the radical. It's not supposed to be. It's being added to the radical, and since it's not a radical term, you can't combine it with a radical, so it should not be a part of the radical. All right. Please try right now problems 3 and 4. You'll notice in number 4 that eventually you're going to get, this is going to end up becoming y to the 3rd, and then you can then use the same property to get rid of the 3 to get the y by itself ultimately. So keep that in mind when you try that. And then over here, you can do some cross multiplying to help you on that one. So give it a shot. All right. Of course, I'll show you the answers here when you hit the play button again. And so go ahead and give that a try. All right. Number 3. We change it to y. We change f of x to y. We interchange the x and the y. So now you have x equal to 2 over y. I intentionally made x into a fraction because we know that when you have a fraction on one side and just a regular term on the other, you can then cross multiply if you make the regular term into a fraction also. If you do that, I end up with x times y on one side, 2 times 1 on the other. You could also multiply both sides by the LCD. You don't have to do that, but that's why I have this additional step right here. You don't need to write that down. If you cross multiply, you can just skip down to here. That's fine. So x times y equal to 2. How do I get the y by itself? Well, since these are just regular monomial terms, with no brackets or anything, you have a red and a green. Remember, when you get the red one by itself, you can divide out now, as long as there's no red ones on the other side. And so that's why I divided by the x to get the y by itself. And a funny answer here, actually. It ends up being equal to the original function. Sometimes that happens. It's rare, but sometimes your inverse function is actually equal to your original function. All right, so the inverse function is equal to that same fraction that we started with. All right. So don't be alarmed by that. That does happen sometimes. Okay, that is possible, as we just discovered. In number 4, all right, again, you change the f of x to y. You then interchange so I get set up here. You then interchange the x and the y. It then looks like this right here. So what I have here after I interchange the x and the y is I realize that I have that my variable is taken to the third power. If your variable is taken to the third power, just like if it's taken to the second power when we were doing the square root property, you guys, if you are able to get the x squared by itself without having a variable on the other side after you get it by itself, then we do the square root property. It's the same thing with this situation here, where if you're able to get the y to the third by itself without having a variable on the other side, remember x doesn't count as a variable here, only the y, because we're trying to get y by itself. All right. What we did with the square root property, though, is we pretended like the entire thing right there, the variable and the square, was just a variable, just a single variable, just like I did here with the x squared being the y. All right. Same thing here. The y cubed would be like a c right there, and then you ask yourself, how would I get the c by itself? Okay, because the c is playing the same role that the y to the third is. All right. The way I would get c by itself is I would add the 1 over, because this is now a linear equation, since c is just to the first power. It's not c to the second or c to the third. So I just add the 1 over. I get this right here, and now the y to the third is by itself. We were able to get y to the third by itself without ending up with a variable on the other side, because x doesn't count in this case, like I said. Then, if you are able to get the variable to the third by itself with a constant on the other side, we can then do this property. And so let's do that right now. The 3 goes away on this side of the equation, and it becomes the cube root over here. All right, the entire other side of the equation has to go underneath that radical. All right, and then now finally y is by itself, because the exponent went away. All right, as that property tells us. Same property we used in problem B right above this. Okay, so the final answer is going to be what? It's going to be, now that you got y by itself, we have f inverse of x equal to this cube root radical. All right. All right. So that is how to figure out what the inverse is equal to. Okay, if they give you an inverse and they say, hey, find the inverse of it, that's how you do it. These last two problems at the very bottom of the sheet here are interesting, certainly. It says if we give you the graph of f now, instead of giving you the f of x like we did in the last 4 problems, if we give you the graph, how do you find the graph of its inverse? All right. Remember I said on the front side of the worksheet, remember I said that with inverse functions, and we just talked about this in the last few problems also, we talked about how the x's and y's interchange. Okay, so the way to find a graph of an inverse, if you already know what the graph of the original function is, they're trying to tell you here that this is the graph of f right here. It says use the graph of f below. So this thing that they graphed already, that's already in front of you, is your f of x graph. Okay, how do you find the inverse graph? Here's how you do it. First of all, what are the points on this current graph? We can use those. All right, they are, let me write it down off to the side here. They are, let's look at it carefully. This one is a negative 3, 1, right? Negative 3, 1. This one right here is 3, 4. And finally, this one is 7, 6. If you count out the marks, there's 7, 6. All right. So here's how it works. I'm going to do the inverse function in red so you can, because they want us to put both graphs on the same grid here. And so I'm going to use different colors here to make sure that it doesn't get hard to read here. For f inverse of x, the points are the same exact 3 points as we had over here, except for the x and y interchanges, because we know that that's what happens when you have inverse functions. All right, so negative 3 comma 1 is now 1 comma negative 3. I just simply switched the x and the y. The 3 and the 4 become 4 and 3. Again, I just switched them. And finally, 7 and 6 become 6 and 7. So let's graph those 3 points. 1 comma negative 3. That is going to be down here. Right there. 4 comma 3. That is going to be right there. And then finally 6 comma 7 is going to be, I just need to make an additional markup here. So that's going to be right there. Okay, don't draw it yet, all right? I know you're thinking, oh, hey, that looks like a line. Let me just draw it. And no, that's not absolutely for sure yet. It's going to work out that way, but that doesn't always work. It's not always that obvious. Here's how you can be absolutely certain that your inverse graph is correct. What you need to do is you need to draw a dotted line similar to the asymptotes from section 9.1, okay? Similar to those axis of symmetry things that you drew in the middle of your parabola in 8.3. It's got to be dotted, okay? But here's how it works. The dotted line has to go through the middle here. It has to go through 0, 0, and it is a line that has a slope of 1, meaning 1 over 1. So that means you go up 1 and over 1 like this, and then you draw a dotted line through those 2 points right there. Okay, so it has a y-intercept of 0, and it has a slope of 1, all right? And it basically creates a dotted line, you guys, that is going to be at a 45-degree angle in between the x-axis and the y-axis right here, if you prefer to think of it that way. But it does have a y-intercept of 0 and a slope of 1. All right, and that's really going to help us here figure out and be certain of it, what the inverse graph is supposed to look like. Okay, so here's how you do it. To find the inverse graph, I need you to turn your page to the side. This is the easiest way to do it. Turn your page to the side so that the dotted line, you guys, is straight up and down, straight up vertical. All right, and then here's how it works. You take the portion of the original graph that is on the left side of the line, and I want you to picture this right now. Imagine what would happen if I just took the part of the line that's on the left side here. It's just this part right here, just the part that's on the left side of the dotted line. Imagine if I took that part of the line and I folded it over the paper. All right, if I folded that portion of the line over, it would look like this, wouldn't it? In other words, it would land on the other side right there. See how it looks like that right there? The portion of the line that's on the left of the dotted line, if I folded that over, imagine, yeah, you don't actually literally have to fold your paper, but if I were to fold the paper over, isn't this where it would land right here? Okay, just the portion right here, not this portion over here. That's on the right side of the dotted line. Just the portion that's on the left, folding that over, this is where it would land. Okay, and it goes right. The reason why I plotted those 2 red points right there is because it's also going to help me figure out where it lands as well. But doesn't it look like it would land right there? All right, so make sure it goes through your 2 points right there, but make sure it looks like you folded it over. Now you just do the same thing on the other side. The portion of the original graph that's on the right side of the dotted line, which is just this part right here. Okay, where would it land if I took that and I folded it over the other direction? I actually folded it over to the other side. It would then look like this right here, wouldn't it? Okay, it will look like that. So this part right here, if I folded it over the dotted line, I actually folded my paper, this is where it would land if I folded it completely over. That is how you draw an inverse graph, all right? The portion that's on this side of on the left side of the dotted line, you fold the paper over. You don't literally have to fold it, but you imagine folding it over. You can fold it if you want, if that helps. But folding it over wherever that lands, that's the first part of the graph. And then you take the portion that's on the right side of the dotted line, you fold that over, okay? And wherever that lands, that's the other part. All right, and that gives you your inverse graph. let's try that one more time here on the last problem. Okay. On the last problem, again, it's very helpful to know what the original points are so that we can use those in the inverse graph. They are, and I know it's kind of hard to see this on one of them. This one right here is going to be negative 1, 1/2. I'll just tell you that. If it was a test question, I would make it more clear what that point is, because it's in between the 0 and the 1 there. So I know that it's not completely clear, but I would make that clear if that was a test question. For now, though, I'll just tell you that that's 1/2. These other points are more clear, though. This one is 0, 1, 1, 2, and 2, 4. It looks very similar to one of our banana problems in section 9.1. In fact, that's where I got it from when I came up with this problem. It's not important that you know that it's a banana problem, though, right now. What's important is that you can come up with the inverse graph. What are going to be the corresponding points for the inverse if these are your 4 original points right here? They are going to be 1/2 negative 1. I just took the first point and I flipped it. Same thing on the other 3. 0, 1 becomes 1, 0. 1, 2 becomes 2, 1. And finally, 2, 4 becomes 4, 2. Okay. So what I'm going to do is I'm going to graph those 4 points, and then I'll work on coming up with the final red graph. But let's do the points first. 1/2, negative 1 is going to be right there. 1, 0 is right here. 2, 1 is right there. And finally, 4, 2 is right there. Okay. Again, it looks like a certain shape is developing here. All right, and you might be thinking, I just want to graph it. All right, but again, math is not about guessing, you guys. It's about being sure about your answers. All right, so let's not just hope that that's the right shape. All right, let's be sure of it, and the way you be sure of it is by doing this dotted line again that I talked about. Y-intercept of 0, a slope of 1. So you rise and run 1. You make your dotted line through those 2 points right there, like this. And then what you do after you make that dotted line is you turn your paper to the side so that dotted line, this is just to help you graph the inverse, all right? You just turn your paper to the side like this so that the dotted line is straight up and down, like that. And then you notice, unlike in the last problem, this problem, the original graph is completely on one side of the dotted line. So you're not going to have 2 different parts this time. You have 2 different parts when your original graph is on both sides of the dotted line. You got to do each part separately. But this time, the graph is completely on the left side, so you just have to fold your paper over 1 time. All right, there's nothing on the right-hand side from the original graph, so you don't fold it from the right over to the left like we did in the first problem. All right, you just do the left side folded over to the right. Where would it land if I folded this over? Use your 4 red points as well to help you guide you along. Isn't it going to land right here? Doesn't that look like where it would land if I folded that over? Okay. It's like they call it a mirror image. Okay. This right here is a mirror image of the original graph. Kind of like with parabolas, where both sides of the parabolas look the same. They look like mirror images. Okay. On both sides of the dotted line. It's a similar type of thing here. The difference being obviously that these two graphs don't connect each other like the 2 sides of a parabola connect, but they do look like they're the same on each side. They're like mirror images of each other. All right. So imagine yourself folding the paper over, and then wherever it lands, that's your inverse graph. Okay, so that concludes section 9.2. We'll be talking more about inverse graphs, at least briefly, in the next section, along with these banana-shaped graphs. We'll be combining those 2 concepts together for a whole brand new concept. But in the meantime, let me know if you have any questions about 9.2. You have a good day, and take care.